Hello, I'm Dr. Andris Bakuzis from Federal University of Goiás, and it's a great pleasure to be here in ICONNANO. I start thanking the organizers for the opportunity to talk a little bit about one of the projects that we are developing in our group. And today I will be talking about membrane-coated nanoparticles for cancer-thermal nanomedicine, from prediction of delivery to survive. Most of the data that I'm going to show you today is related to a recent publication of our group in molecular pharmaceutics. So if you're interested for more detail, please take a look there. We have here a multidisciplinary team and people from Federal University of Goiás and also from Unesp, State University of São Paulo. This work is related to the PhD thesis under my supervision, Dr. Ailton Souza Jr. So this is the summary of my talk. I would start first by talking about the motivation that led us to start to work with this membrane camouflage strategy. I will then show you data of the synthesis and the characterization of the membrane-coated magnetofluorescence nanoparticle that will be working at the first biological window in the near infrared region. Later, I will show you pharmacokinetics data with two murine tumor models in Ehrlich, which is a breast murine tumor, and a sarcoma model, which is S180. I will show you the delivery efficiency predictive model, how do we solve a free compartment model, and also we present data showing how we can modulate the tumor microenvironment and increase actually the delivery efficiency with that. And finally, I will finish by showing a photothermal preclinical study after nanoparticle systemic administration. In this case, I will be only showing you data with the murine tumor model S180 and finish with my conclusions. So let me first start by talking about cancer thermal medicine. There are three societies that work with thermal medicine applied to cancer, to oncology. The Asian Hyperthermic Oncology, European Society of Hyperthermic Oncology, and the Society for Thermal Medicine. So they are around for 20 to 30 years, and they have already developed equipments that work for thermal medicine, that treat cancer with heat by several mechanisms like microwave ablation, radiofrequency ablation, and they do use this technology even together with MRI, doing MRI thermometry. This system here is for superficial tumors, and basically what they had observed is that they increase the efficiency of treating cancer if they couple it together with radiation. So there is a synergy between radiation therapy and hyperthermia. And why that happens? That happens because when you are a certain temperature range, which is around 43 degrees Celsius, you notice, people had noticed, those societies had noticed in those years that you can, at this condition, increase the blood flow and vessel permeability. What happens then is that you improve the oxygenation within the tumor, and that's why you have a benefit together with radiotherapy, the synergy with radiotherapy. You also have a synergy with chemotherapy from several types of drugs. That happens because with temperature, there is an increase in the fluidity and the permeability of the drugs inside the membranes. You also have very interesting mechanisms related to DNA repair. So hyperthermia affects DNA damage repair pathways. This might induce apoptosis. And more recently, there is a great interest on controlling the temperature, the heat dose, the thermal dose, in a way to activate the immune system. So this is one of the things that are under study by all the communities in this field. It is well known from electromagnetic theory, together with the first law from dynamics, that heat can be generated using electromagnetic energy by three mechanisms. Those mechanisms are the free current loss, the dielectric loss, and the hysteresis loss. In these videos here, you're seeing what is happening with thermal nanomedicine. In one case, we're talking about photothermal therapy, where electromagnetic radiation is interacting with nanoparticles. You saw an increase of heat in this case. Or in the case here, where AC magnetic fields are interacting with the magnetic moments of nanoparticles. In this case, you also have a generation heat that is arising from this term here. So what I have discussed with you before was related to intratumor applications. What happens if you introduce systemically the nanoparticles? So this is a movie of our group where we do show an accumulation of nanoparticles in the tumor region. Well, this has been shown before. Maeda had shown that before and related it to the EPR effect. And actually within the EPR effect, there is a passive targeting, which is believed was believed to be related to some fenestrations a long time ago. And this was a great promise for drug delivery. And actually Doxil, Ibrexane appeared within the market with that promises that this would be very good for treating cancer in human patients. There was a review by Dr. Chen, Warren Chen, the group of Dr. Chen, that really surprised everybody that the delivery efficiency of these nanoparticles had not seemed to be changed significantly during the years. He found around 0.7%, but notice that there are fluctuations here and there are cases that would be around 10%. Nowadays, there are a lot of criticisms regarding this EPR effect. Some of them are talking that this does not happen in humans. The reason why it does not happen in humans is that murine tumors actually increase very fast in comparison with human ones. So there are the possibility, this was believed, or there were the possibility to having those fenestrations there in murine tumors, which does not occur in most of the human tumors. And this is discussed in several papers. More recently, we even found that even in animals, fenestrations does not play that role that was believed to be. In another paper from Warren Chen last year, it was discovered that actually the mechanism of entry of nanoparticles to solid tumors is through an active process. So fenestrations are not that important. But anyway, it is interesting that those type of models can reveal some aspects that are worthy to be investigated. So we know that Doxil has a long blood circulation time, and this was observed in animals. It's observed in animals as it appears in humans too. And in fact, inspired in the EPR effect, we discovered several ways to enhance intratumor delivery of therapeutic agents. This is very, very interesting because although fenestration does not seem to be the play role, we found out ways to increase this delivery efficiency by several factors. One of them we would be using here in our work to test our model. So the mission of our group is to develop multifunctional magnetic nanocarriers for thermal nanomedicine applications. We are using several strategies for that, always using magnetic nanoparticles. Some of them just the magnetic nanoparticles, manganese ferrite nanoparticles. Some of them we develop more sophisticated systems that are able to be used for magnetic hyperthermia, photothermia, and also luminescent nanothermometry. But mainly, the two strategies that we had developed as the movie that you had seen was our albumin coating, where the near-infrared molecule is actually coupled to albumin. This is one of the strategy. And the other one that I will be discussing here, it's actually to introduce a near-infrared molecule into the membrane and perform this membrane camouflage nanocarriers that I will be discussing right now, which was related actually to the thesis of Ailton, as discussed previously. The membrane-coated nanoparticles that we are discussing is actually a biomimetic design strategy. And this type of strategy has started a long time ago. In the 90s, Dr. Giquard from France had even named the red blood cells coating as nanoerythrosome. The idea here was that they could observe a very long blood circulation time since erythrocytes stay in the blood for around 100 days. Well, they had not proved this, but it was only in 2011 that a group in California, led by Dr. Zhang, proved that they had successfully coated the PLEJ nanoparticles with a red blood cell membrane, and that even this has a longer time blood circulation in comparison to pegylated nanoparticles. Well, notice that these source cells, the way that they interact in vivo, it's actually through membranes. There are a lot of opportunities here because you can change the source cells, change the nanoparticle cores, and build a cell membrane coated nanoparticle for several types of strategies. One of them, for instance, is to target metastasis. So it's a great opportunity here. You can sometimes use the patient cells. So using the patient cells, it is believed that we might be able to do some personalized medicine in the near future. Of course, there are a lot of challenges, but the future seems great in this type of strategy. So what's the goal of our approach? So basically, we wanted to develop a system that has low systemic clearance. Of course, this means that would result in a long blood circulation time. We wanted to show if this could result in enhanced tumor uptake. This is something that is believed to happen. We wanted to develop a system that we were able to do optical and magnetic imaging, in particular with fluorescence molecular tomography and alternating current biosusceptometry, which I will not be showing here, but we have shown that ACB can be used too for this system. Just take a look in our paper. And we wanted also a system that could be used for optical and magnetic concept treatment modalities for nanomedicine, as photothermotherapy and magnetic hyperthermia. So to do that, we developed a strategy where we have the magnetic nanoparticles, which we choose the manganese ferrite, which are very good for ACB. We choose the IR 780 for the near-infrared, which we are able to observe by FMT, as the movies that I showed you before. And we then coated it with the membrane, with the red blood membrane. I should make some comments here that the incorporation of magnetic nanoparticles in red blood cells is not new. There is a group in Italy that has done this before regarding just the magnetic nanoparticles into red blood cells, not coating the nanoparticles per se. There is another paper regarding the use of ICG, coupling ICG to red blood cells, so to the membranes of red blood cells. ICG is the first member of this family here, so this is a new generation. ICG is the only new infrared imaging system in the market, actually, for clinical applications. So there was this, but notice that there was no magnetic nanoparticles here. And I should also mention, I'd like to mention that the first idea in our group to develop a system with magnetic nanoparticles into RBC actually came from Dr. Mendanha. He was at the time a PhD student, and later I discussed with him the possibility to incorporate IR 780, and together, after he finished his PhD and entered in our physics department, we decided to work with Ailton to develop this type of nanoparticle preparation. Okay, so to do this nanoparticle, we start first with the erythrocytes. We do a hypotonic swelling, so we separate the erythrocyte membranes. We then mix it with the magnetic fluid that has the nanoparticles and the fluorescence dye, which is IR 780. With that, we get a sample where inside the membranes you can see the magnetic nanoparticles. This is a movie an image movie, an optical image movie in a microscope, where we are putting close to the sample the magnet. So there is a magnetic force, and you can see inside some magnetic nanoparticles. This is not the nanocarrier yet. To get the nanocarrier, we need to do a extrusion process. Just after the extrusion process, we can actually pass through a chromatography column and separate nanostructures, as I will be showing you in the next slide. So as I told you before, just after the extrusion process that we obtain nanostructures. So this is an image from transmission electron microscopy of our sample. We can pass through the chromatography column and then separate some fractions here. So F2, F3, F4, F5 is related to those fractions. And we can characterize the nanoparticle size using nanoparticle tracking analysis, we found around 100 nanometers. We can also measure the amount of protein that we have in the membrane. So you see that this is the control, this is the one with fraction free, and we can also check what is inside the nanoparticles, and we do that by EDS, and we prove that there is iron and manganese there. So there are the magnetic nanoparticles are there too. Separating these fractions, we can go to the fluorescence molecular tomography and check for the fluorescence of those samples. So we see here that the highest fluorescence is appearing for F2. And we also separate the samples and do vibrating sample magnetometer. So we do a magnetic characterization. What you see here is those fractions. So you see that this for here, this F2 is the one that has the highest magnetic moment. So it also has the highest amount of magnetic nanoparticles inside. We also did absorbance study. So here it's IR 780. As expected, there is a peak here in this near infrared range. So if you have the red blood cells with IR 780, you do see this term here. The magnetic nanoparticles is the black term. You don't see anything. But when you put them all together, which is our sample, you do see a peak here, which is related exactly to the IR 780 that was incorporated together with the magnetic nanoparticles, forming our nanostructures. This here you see the characterization with the zeta potential. So first, the magnetic nanoparticles were citrate coated, and when you incorporate them into RBC membranes, you get this term here. And this is very close to what you have together with IR 780 and the RBC membranes as expected. We also performed photothermal analysis. In this case here, we are just showing the ones of the sample with RBC and IR 780 without the magnetic nanoparticles. And we did one with our samples with the magnetic nanoparticles for magnetic hyperthermia. And this is the increase of temperature for different field amplitudes at 330 kilohertz, showing that there is potential for magnetic hyperthermia too. So to perform our pharmacokinetic studies, we used Ehrlich and S180 murine tumor models. The mice is the Swiss mice, which is an immunocompetent outbred, and we perform a heteroorbital administration. We are using a different strategy from the literature. It is a fluorescence molecular tomography approach. In this case, it is a non-invasive strategy. And to do the pharmacokinetics, what we do, we monitor what is in the tail. That's why we do heteroorbital, so we can monitor the amount of this nanocarrier in the blood by monitoring the amount in the tail. And we monitor the delivery, the intratumoral delivery, by also putting a ROI in the tumor region. So with that, we get this pharmacokinetic profile here. To simulate what's going on in our animal, we separate this in a three compartment model. One is the central, related to blood circulation. Another one is the peripheral, which is related to all the other organs. And we have a third compartment, which is related to the tumor. By using first order kinetics, by assuming first order kinetics, we are able to write down the equations for this compartment model, and those are the experimental conditions. We perform the study by solving this analytically and also by doing numerical simulations with a well-known software from the literature for PK analysis, which is named as MonoLix. The results from MonoLix are compared with our analytical solutions, which we demonstrate that is related to those three exponentials here, and with these terms here, these parameters actually coupled by these three equations, which are the constraints that correlates those lambda 1, lambda 2, lambda 3 with those K10, K12, K23, K31, and K13 parameters. So for the pharmacokinetic studies, we use a control 3 IR 780, which is compared with our nanoparticles. So obtaining by fluorescence molecular tomography the pharmacokinetics, which is for red, the data in red is for the blood, the blue is the tumor, okay? From this data, we solve numerically using MonoLix and obtain those parameters here. We also compare these numerical simulations with our analytical solutions, and you do see here in dash that the solutions are equivalent, showing that the analytical solutions that we obtain are very good. And the other thing that you can observe that is that the intratumoral delivery of the magnetic nanoparticle is higher than the free IR 780. So the values that we were obtaining for delivery efficiency of the magnetic nanocarriers was quite high. And to check that if this was really happening, we also did a histopathology analysis, pairs staining. So here you have the control, is the liver, the spleen, the kidneys, the lungs, and the tumor. And this is the magnetic nanoparticle 72 hours, and this is 120 hours. The arrows here indicate in blue where there is iron. and this is correlated with the magnetic nanoparticles. So we do observe a lot of magnetic nanoparticles in the spleen for this type of nanocarrier. We do see a little bit in the liver too, and we see a lot too in the tumor, which corroborates with our conclusion that we have a system that had increased a lot the delivery efficiencies to the tumor. Well, after showing that this three-compartment model, the numerical simulations, were equivalent to our analytical solutions, we were able to start to see what does the analytical solutions can tell us. And one of the things that we found out was if one of the parameters here is very high in comparison with the others, this approximation is valid, and we can find out what is, for instance, the time at which you will have the highest delivery efficiency. And this information is very interesting for several persons that are doing this type of pharmacokinetics, because as far as I know, this is the first time that this appears in the literature, correlating those parameters here. So in principle, this could be valid for any type of nanoparticle. So other groups could use these expressions to check the maximum and the maximum delivery to in various systems. This type of solution actually reminds us a lot an approach in the literature which uses a mechanistic model, which was developed by a group in MIT to investigate how antibodies get into the tumor. And by making a comparison between both models, we were also able to correlate the term K13 here with the permeability and find out a value which is very close to the value expected from the literature for this type of marine model. Well, we then decided to move a little bit forward. We wanted to test our model, and we knew from the literature that it was possible to modulate the tumor microenvironment with losartan. This is actually a group from Harvard, led by Dr. Jain, that showed that with losartan we can increase significantly the amount of drug into the tumor. So we decided to make an experiment similar to what Dr. Jain has done before, using losartan, and check what would be our predictions and the results that we get to test the model. So to perform the analysis of tumor microenvironment modulation, we changed the model. We use S180 with losartan. So the symbols here are the experimental data. This one here is the sample without losartan, and this is our analysis, our theoretic analysis of the tumor delivery efficiency. By using the analysis of Jain, we predicted that in the dashed line, that's what would happen with the delivery efficiency with losartan. And what we found out was the symbols, the triangle symbols that you are seeing here, which is very good, in good agreement with what we observed experimentally. In fact, one of the things that we can say is that the delivery efficiency of our case here, which is sarcoma that we are showing here, is lower than the case for Ehrlich. So this means that the tumor heterogeneity plays a role. So there are different tumors, and the capacity to deliver would be different in those two tumors. However, it is clear that we can enhance, as Jain observed, with losartan, the delivery efficiency of the nanocarrier. And by analyzing those parameters here, we are actually able to conclude that we had a 2.15 times enhancement in the perfusion of the animals when treated with losartan. After the pharmacokinetic studies in the sarcoma group, we decided to go for a photothermal preclinical study of the systemic administrated group. And what you're seeing here is a setup of our experiment. So you can see the near-infrared laser, you can see the mouse, and we are monitoring the temperature with the thermal camera with a very small angle in order to guarantee a precise temperature measurement. You can see here that the temperature measured in the tumor region is very high, while if you go in another region of the animal, there is no heat generation because there are no nanoparticles in that region there. So for this study, we have a group of females that we have just administered the magnetic nanoparticles. We have also a group of females with N equals 5 that had passed through losartan, and another group, but now of males of 4 animals, showing altogether 13 animals that were investigated. And here's the curve of the temperature as function of time. We have a ROI where we measure the temperature, and this is a snapshot of what's happening, increasing the time. So you're seeing, as we saw in that movie, an increase in the temperature. And this is the profile that you have for all the animals. So because they are all different, the temperature profile is different. Only one animal, we observe a very high increase here, and we didn't want to pass to 55, and we modulated the laser power in this case. The other ones was all in the same condition. And with that, we were also able to monitor what would happen with the tumor volume as a function of time after the procedure, after the treatment. We do see a complete regression for this group here, this one here also, and this one here. Notice that we have 3 animals here, not 4. The reason is that we actually observe for one of the animals recurrence that we will discuss very soon. And basically, all of them, we are able to do a thermodose analysis. We decided to perform a CEM 50. CEM means cumulative equivalent minutes at 50 degrees Celsius. And this can indicate how is the thermodose within the animals. The thermodose within them was quite different between all those animals groups. However, it was enough for us to see complete tumor regression. So as mentioned before, in one of the groups, we noticed that there was a tumor recurrence. This animal here surprised us a little bit because the thermodose was the highest in this group. We also did an histopathology analysis after we sacrificed the animal. We did observe that there were nanoparticles there, quite a lot. That explains why we had a very high thermodose. And the reason why we believe that this animal showed tumor recurrence is that tumors are actually heterogeneous, and although we had a very nice heat or temperature increase in certain places in the tumor, there certainly were other regions because of the heterogeneity of the tumor that did not receive enough thermodose to kill the tumor cells, and that's why it recovered, and eventually we had to sacrifice the animal because the tumor were very large. So we investigated 13 animals. One of the animals actually died after the procedure. We don't know the reason why. Another animal we had to sacrifice because it observed tumor regression. But this is the Kaplan-Meier curve of the control, and this is our results here showing that the photothermal preclinical study after administration has an 85% of survival for this membrane camouflage magnetic nanoparticle, which is very, very good for sarcoma 180. I just noticed that I'm almost out of time, so in conclusion, very fast, we had successfully synthesized this membrane camouflage magnetofluorescent nanoparticles. We had developed a predictive model for intratumor delivery efficiencies, which can be useful for several other groups. There are expressions here for the time of highest delivery efficiency. We also showed that the photothermal preclinical study after nanoparticle systemic administration, great survival rate using this type of magnetic nanocarriers. So to finish, I would like to thank you all for hearing my presentation, and of course the financial support that we have been receiving by the Brazilian agencies which support our investigations. Thank you all, and I'm ready for any questions if you have.